Humanity's greatest construction project waits just beyond our atmosphere. This is not a fantasy from a distant future, but a staggering engineering puzzle we can already begin to solve. The ultimate goal is a Dyson swarm, a vast constellation of machines built to capture the nearly unimaginable energy of our sun. The dream has always crashed against one brutal reality: the sheer amount of material required. To build such a thing from the resources of Earth or even our moon would demand moving entire mountains into space, an effort so vast it drains the dream of all hope. But what if the solution is not to haul material up from the depths of a gravity well, but to use what is already floating freely in the void? Scattered throughout the inner solar system are countless near-Earth asteroids, rocky and metallic bodies containing all the raw ingredients we would ever need. This changes everything. The challenge transforms from one of impossible mining into one of precise capture and sophisticated processing. By the end of this exploration, you will possess a complete, step-by-step blueprint for how our civilization could realistically construct this megastructure, turning science fiction into a working project plan. We will uncover how to redirect asteroids, how to build factories that can self-replicate in the darkness, and how to manage a swarm of billions of satellites without them colliding. What does it truly mean for a species to harness the power of its star? This immense structure we envision is not a single, solid sphere. That classic image of a rigid shell encasing the sun belongs to science fiction, a beautiful but impossible idea. The gravitational and mechanical forces involved would tear any such shell apart. The realistic, achievable version is something far more elegant and alive: a Dyson swarm. Picture our solar system not as a collection of planets, but as a vast, empty construction site. Into that emptiness, we would begin placing individual units, each one a sophisticated solar power station or a specialized manufacturing hub. These units would not be connected physically. They would fly in independent orbits around the sun, like a colossal cloud of intelligent bees around a hive. Collectively, they form the swarm, a dynamic and flexible megastructure. The scale of this endeavor is almost beyond human comprehension. To capture even a modest fraction of the sun's total energy output, the combined surface area of all these satellites would need to be millions of times greater than the entire surface area of Earth. We are talking about constructing a new, artificial surface in space so vast it could wrap around our planet millions of times over. The energy harvested would be on a scale we can barely grasp, orders of magnitude beyond everything our global civilization currently uses, powers, and dreams of. It represents not just an upgrade, but a fundamental transition in what a civilization is capable of. This swarm architecture solves the fundamental problems of the solid shell. Because each unit is independent, construction can be incremental. We don't need to build the entire thing at once. We can start with one station, then 10, then 1,000, growing the swarm over centuries. Each new unit adds to the whole, immediately producing useful power and materials to build the next. There are no impossible structural stresses, just the delicate ballet of orbital mechanics, managing the paths of billions of individual pieces so they never collide. The swarm is not a static monument. It is a growing, breathing ecosystem of machines, and its first building blocks are already within our reach, waiting in the dark. The numbers alone reveal a truth we cannot escape. To build even a modest Dyson swarm, we would need to process an amount of raw material so vast it defies easy comparison. We are not talking about mining a few mountains or emptying a single ocean. The most conservative estimates suggest we would require a mass equivalent to a large planet, something on the order of the entire planet Mercury, processed and launched into precise solar orbits. This is the scale of the ambition, and it presents our first and greatest obstacle, the gravity well of Earth itself. every single kilogram of material we wish to use in space must first be wrestled free from our planet's powerful gravitational grip. Even with revolutionary launch systems like space elevators or mass drivers, the sheer energy cost of lifting a planet's worth of material from the bottom of this deep well is catastrophically prohibitive. It would consume more energy than our entire civilization produces in millennia, essentially making the project a paradox. You would need the energy of a Dyson swarm to build the Dyson swarm. This is the fundamental bottleneck that has long kept the concept in the realm of fantasy. The lunar surface offers no real reprieve. While the moon's gravity is weaker, its material is still locked at the bottom of a significant gravity well, one that would require immense infrastructure to escape in bulk. We would be trading one colossal excavation project for another, still facing the monumental task of moving astronomical amounts of rock and metal. The conclusion is inescapable. If we are to build a structure of planetary scale, we cannot afford to be planetary miners. We must become architects of the void, using resources that are already weightless and in motion. This shifts our gaze from the ground beneath our feet to the dark roads already traced around our sun, where the construction materials for our future are not buried but sailing freely, waiting to be claimed. The answer to this material paradox is already drifting through the solar system. A vast population of natural resources, known as near-Earth objects, follows orbits that periodically bring them close to our own planet. Unlike the distant asteroids of the main belt, which lie between Mars and Jupiter, these objects are our celestial neighbors, passing within what astronomers consider our local cosmic neighborhood. This proximity is the key that unlocks the entire endeavor, drastically reducing the energy needed to reach them compared to any destination on a planetary surface. We are not looking at a handful of distant rocks, but a rich and varied population. Current estimates suggest there are over 30,000 known near-Earth asteroids, with countless more awaiting discovery. They range in size from small boulders just a few meters across to colossal worldlets several kilometers in diameter. While each individual asteroid might seem insignificant, their combined mass is staggering, totaling many times more than all the material humanity has ever launched into space. More important than their sheer number is what they are made of. Their compositions read like a catalog of industrial essentials. Metallic asteroids, often the fragmented cores of ancient protoplanets, are rich in iron, nickel, and cobalt, the very backbone of any structural framework. Stony asteroids provide abundant silicon and oxygen, the fundamental ingredients for glass, solar panels, and the very air we would need for any permanent habitats. Carbonaceous asteroids are treasure troves of water ice, carbon, and complex organic compounds, offering not just life support but the feedstocks for advanced polymers and materials. Every essential element for building a civilization in space, from the girders of a power station to the soil of a garden dome, is already out there, pre-packaged and in a zero-gravity environment. This transforms our task from one of impossible extraction into one of sophisticated selection and retrieval. We are not starting from scratch, we are shopping in a well-stocked, if somewhat scattered, warehouse. Before we can build, we must learn to see. The first true step toward a Dyson swarm is not a launch but a survey, a grand and meticulous cosmic census. We need to transform those thousands of anonymous dots of light into a detailed inventory, a catalog of every potential construction site and resource depot drifting through the inner solar system. This requires a new generation of eyes in the sky, purpose-built for this immense task. While missions like the upcoming NEO Surveyor are pioneering this work for planetary defense, our ambition demands something far more comprehensive. We would need a constellation of dedicated space telescopes, positioned in orbits that give them an unobstructed, perpetual view of the heavens, free from the distortion of Earth's atmosphere and the cycle of day and night. Their sole mission would be to scan, track, and analyze, not just to find asteroids, but to understand them intimately. Finding an object is only the beginning. The critical work lies in characterization. For our purposes, every asteroid must be assessed against a strict set of criteria. First, its orbit. We need to know its precise path with extraordinary accuracy, predicting its position decades or even centuries into the future. Is its trajectory stable? How much energy would be required to nudge it toward a useful construction orbit? Second, its physical properties. What is its size, shape, and mass? A lumpy, spinning rock presents different challenges than a dense, metallic sphere. But the most vital piece of information is composition. What is it made of? This is where spectral analysis becomes our most powerful tool. By studying the precise colors of sunlight reflected off an asteroid's surface, we can determine its spectral type, essentially reading its elemental fingerprint. Is it a dark, carbon-rich C-type packed with water and organic compounds? A stony S-type, abundant in silicon and metals, or the prized M-type, a metallic remnant of an ancient planetary core, a mountain of high-grade steel already floating in space? This phase is not about abstract science, it is logistics. We are creating a detailed manifest of available construction feedstock, tagging each celestial asset with its potential use. A carbonaceous asteroid becomes a future reservoir for water and plastics. A metallic one is earmarked for structural beams and machinery. This vast, quiet effort of mapping and measurement lays the indispensable foundation for everything that follows, turning a sky full of anonymous rocks into a verified portfolio of resources, waiting for the call to be put to work. With our celestial inventory complete, the real work begins. We have identified the perfect asteroid, a metallic M-type rich in iron and nickel, its orbit charted with precision. But it is not where we need it to be. Its natural path is a long, elliptical loop around the Sun, a road that only occasionally brings it near our proposed construction zone. We cannot build a stable power grid on a foundation that wanders wildly through space. This is the capture problem, the monumental task of celestial logistics, where we must learn to gently but irrevocably alter the paths of mountains. The goal is not to drag the asteroid to Earth, but to guide it into a new, useful solar orbit, a kind of cosmic parking lot. Ideal locations would be stable points in space, like the Earth-Sun Lagrange points, where the gravitational pulls of the Sun and our planet balance out. These regions become natural hubs, places where processed materials and finished components can accumulate without constantly fighting gravity. Getting an asteroid there, however, requires a fundamental change to its momentum, a nudge against the immense clockwork of the solar system. The brute force approach of powerful rockets is completely impractical. The fuel required would outweigh the asteroid itself. Instead, we must think in terms of persistent, gentle persuasion. This is the domain of low-thrust, high-efficiency propulsion. Imagine a spacecraft perhaps no larger than a car, latching onto the surface of a mountain. Instead of roaring engines, it emits a faint, steady blue glow, an ion drive. By electrically charging atoms of xenon gas and expelling them at tremendous speed, it creates a whisper of thrust. That whisper, sustained for years without stopping, builds up. Over a decade, this constant, gentle pressure can alter an asteroid's velocity by enough to reshape its entire multi-year orbit. Another elegant tool is the solar sail, a vast, reflective sheet thinner than a human hair. With no fuel at all, it uses the physical pressure of sunlight itself, the gentle push of photons, to generate thrust. Unfurled near an asteroid, it acts as a cosmic windmill, slowly but surely changing its course. For the largest asteroids, the most efficient method might be to turn the asteroid itself into its own engine. This is where mass drivers come in. Picture a long electromagnetic railgun installed on the asteroid's surface. It would scoop up loose material from the ground, accelerate it to incredible speeds using solar power, and hurl it into space like a continuous stream of bullets. According to Newton's third law, every action has an equal and opposite reaction. By throwing mass in one direction, the asteroid is pushed in the other. The asteroid literally propels itself by throwing bits of itself away, a slow, steady process of self-propelled rearrangement. The defining characteristic of all these methods is time. We are not executing a rapid capture, we are initiating a celestial migration, moving a single sizable asteroid into its designated processing orbit could take anywhere from 10 to 50 years. This forces a profound shift in planning perspective. The architects of this project would not see their work completed in a lifetime. They would be planting trees whose shade they would never sit under. Each asteroid we successfully redirect is a gift to a future generation, a mountain of raw material delivered to the factory gates of a civilization still taking shape. It is a testament to patience on a scale humanity rarely contemplates, where the most powerful force is not a sudden explosion, but the unwavering persistence of a faint, blue glow in the endless dark. A mountain of steel now drifts silently in its new orbit, a dormant giant awaiting its purpose. Here on Earth, mining is a brutal, gravity-driven affair of colossal machines, deep pits, and immense environmental cost. But in the airless, weightless realm of space, the rules of industry are rewritten entirely. Mining an asteroid bears almost no resemblance to its terrestrial counterpart. It is a precise, surgical disassembly conducted in a vacuum where there is no up or down, where a misplaced shove can send 1,000,000 tons of valuable ore drifting irretrievably into the void. The first challenge is simply anchoring ourselves to the surface. An asteroid's gravity is so negligible it is effectively zero. A gentle hop would launch you on an endless journey. Machinery must be physically bolted or anchored to the rock, and every action must be carefully counterbalanced. Instead of giant excavators, think of sophisticated robotic arms equipped with jackhammers, grinders, and cutters, all designed to operate in extreme temperature swings and lethal radiation. These would be teleoperated from the safety of an orbiting habitat or, more likely, fully autonomous, guided by artificial intelligence that can adapt to the unpredictable contours of an alien landscape. The techniques for processing the material are equally alien. For a metallic asteroid, the most valuable resource is pure metal. One elegant method is magnetic separation. As robotic crushers pulverize the surface regolith into a fine dust, this powder is passed through powerful magnetic fields. Grains of iron and nickel are pulled from the stream, while non-magnetic rocky slag is diverted away. What remains is a ready supply of high-grade metal powder, perfect for feeding into space-based three-dimensional printers or sintering into solid beams. For carbonaceous asteroids, the prize is water and volatile compounds locked within the rock. Here, thermal processing comes into play. Mined chunks of asteroid material are placed inside sealed, mirrored ovens. Concentrated sunlight, focused by vast parabolic mirrors, heats the rock to high temperatures. This baking process, called pyrolysis, drives off the trapped water ice and other volatiles as vapor, which is then captured and condensed in cooled chambers. The water can be split into hydrogen and oxygen for rocket fuel and breathable air, while the carbon-rich residues become feedstocks for manufacturing plastics and other synthetic materials. But how do you contain and manage these processes without gravity? You cannot simply pour liquid metal into a mold or let sediment settle in a tank. The solution is to create artificial gravity where you need it through rotation. Imagine a facility constructed from the first asteroid's processed materials, shaped not as a static base but as a spinning cylinder or a pair of counter-rotating rings. Inside this rotating frame, centrifugal force pins materials and fluids to the outer wall, creating a predictable, controllable environment. Here, more familiar industrial techniques become possible. Molten metals can be cast, chemicals can be separated in settling tanks, and delicate assembly work can be performed with ease. This rotating factory becomes the heart of the operation, a place where raw asteroid feedstock is transformed into finished, functional components, from solar panel arrays to the structural frames of new power stations. The scale of this endeavor presents its own profound challenge. To build a swarm of billions of units, we cannot possibly launch all the necessary mining and factory equipment from Earth. The logistics chain would be impossibly long and fragile. This is where a revolutionary concept known as the seed factory changes the game entirely. The idea is to launch from Earth not a complete industrial plant, but a minimal, self-contained starter kit. This initial seed would contain a core set of versatile machines, perhaps a three-dimensional metal printer, a solar panel fabricator, a computer chip etching unit, and a robotic assembly arm. Crucially, this seed factory is designed with one ultimate purpose: to build more machines. Using the raw materials from its first captured asteroid, it would not just produce solar satellites, it would painstakingly manufacture copies of its own components. One 3D printer would build the parts for a second printer. One assembly arm would help construct a second arm. Slowly, iteratively, the factory would undergo a form of mechanical reproduction, growing from one facility into 2, then 4, then 8. This exponential scaling is the only way such a project becomes feasible. The seed factory is the catalyst, a tiny speck of industrial DNA planted in the resource-rich soil of space, programmed to grow into an entire ecosystem of production. It turns the asteroid itself into both the quarry and the quarry's machinery, a closed loop of creation that builds the future from the bones of the ancient past. The mountain has been tamed, its raw ore now a fine, magnetic dust drifting in containment chambers. But this dust is not yet a building block, it is merely potential. To forge a civilization from asteroids, we must master the alchemy of the void, transforming this anonymous regolith into the pure, standardized ingredients of industry. This is primary processing, the vital bridge between mining and manufacturing, where chemistry and focused sunlight perform a kind of elemental purification. Take that cloud of metallic dust rich in iron oxide. In a traditional Earth-based blast furnace, we would use carbon to rip the oxygen away, a dirty and energy-intensive process. In space, we have a cleaner, more abundant reagent, solar electricity. Through a process called molten regolith electrolysis, the dust is melted in a container using nothing but concentrated sunlight. Then an electric current is passed through the molten soup. The oxygen atoms, negatively charged, migrate to one electrode and bubble off as pure, breathable gas, a vital byproduct. What remains at the other electrode is a pool of pure, molten iron or nickel, ready to be cast. This elegant process does two critical jobs at once. It produces high-purity metal and captures life-giving oxygen, turning what was once rocky waste into two fundamental resources. For silicon, the heart of every solar panel and computer chip, a different ancient technique finds new purpose. Carbothermal reduction might sound complex, but its principle is simple. Silicon is tightly bound to oxygen in rocks, forming silica. To free it, we mix the crushed silicate ore with a source of carbon, often derived from the same carbonaceous asteroids that provide water. In a solar furnace, this mixture is heated to extreme temperatures, around 2000 degrees Celsius. At that heat, the carbon greedily grabs the oxygen atoms, forming carbon monoxide gas and leaving behind molten, elemental silicon. This liquid silicon can then be carefully cooled and shaped into pristine ingots, the pure crystalline feedstock from which entire industries will grow. But raw ingots and molten pools are not yet a construction site. The final step of primary processing is standardization. The output must be predictable, uniform, and easy to handle in zero gravity. That molten iron might be spun into fine, spherical powder, perfect for a three-dimensional printer's feedstock hopper, or it could be drawn into long, continuous strands of wire, spooled for later use in electrical systems or as reinforcement. The silicon ingots might be vaporized and deposited onto thin, flexible sheets to create photovoltaic films. The leftover silica from various processes, essentially high-purity glass, could be formed into vast, transparent panes or spun into fiberglass for insulation and composites. Every output is designed for the next stage. Each powder grain, each spool of wire, each glassy sheet is a modular component in a grander assembly. The entire symphony of this primary processing stage is conducted by a single, relentless conductor, the sun itself. Massive, curved mirrors, kilometers across and thinner than a soap bubble, would focus raw sunlight onto reaction chambers and furnaces. There are no fossil fuels to burn, no complex nuclear reactors to manage at this stage, just the clean, immense heat of our star harnessed with silent, passive precision. This solar-centric approach is not just efficient, it is philosophically fitting. We are using the very energy we aim to capture to bootstrap the machinery that will capture it, a beautiful closed loop beginning to form in the darkness. The asteroid is no longer a rock, it is a refinery, its heart glowing with borrowed sunlight, methodically breaking down the old world to assemble the bones of the new. Pure metal powder and silicon ingots are now the new raw materials of space, but they are still just raw materials. To become a civilization, they must be assembled, shaped into the intricate components of a power grid that spans a star. This is the realm of in-space manufacturing, a discipline that operates under a completely alien set of rules, free from the two dominant forces that shape industry on Earth, gravity and atmosphere. In the pristine vacuum of space, under the gentle tug of microgravity, we can build in ways that are simply impossible on our home planet. The workhorse of this new industrial age is additive manufacturing, more commonly known as three-dimensional printing. But forget the small plastic trinkets of earthbound printers. In space, these machines work with the very essence of the asteroids themselves. Imagine a robotic printer, anchored to the frame of our rotating factory, its hopper filled with that fine, spherical iron powder we refined. Instead of using heat from a nozzle, it employs a high-powered laser or electron beam. This beam sweeps across a thin layer of powder, meticulously fusing the metallic grains together into a solid, predefined shape. Layer by minuscule layer, a complex component emerges from the dust, a structural bracket, a gear for a robotic arm, or a segment of a load-bearing truss. The beauty of this process in microgravity is its freedom from sagging or deformation. A structure can be built from any angle, creating intricate internal lattices and geometries that would collapse under their own weight on Earth. This allows for astonishing strength with minimal material, a principle known as topological optimization. We are not building solid blocks, we are building skeletal frameworks as strong as steel but as light as bone, perfect for the mass-conscious economy of spaceflight. For creating large, seamless surfaces, other techniques come to the fore. Vapor deposition is a kind of atomic-scale painting. In a vacuum chamber, a source material, like pure silicon, is heated until it turns into a vapor. This vapor then condenses evenly onto a rotating substrate, perhaps a thin, flexible polymer film unspooled from a reel. The result is a perfect, uniform coating, creating vast, roll-to-roll sheets of photovoltaic material or protective mirror surfaces. Another method, spin forming, takes advantage of microgravity's lack of a down. A blob of molten glass or metal is injected into the center of a spinning frame. Centrifugal force created by the spin pushes the material outward in a perfectly even sheet, like a cosmic potter throwing a clay plate. This can produce flawless, gossamer thin membranes kilometers across, thinner than a soap bubble yet perfectly flat. These are the kinds of structures that define the Dyson swarm, ultra-thin solar reflectors that focus sunlight onto power stations, or immense, lightweight photovoltaic films that capture it directly. Such delicate, expansive architectures could never survive the violent stresses of a rocket launch from Earth's surface. They are children of the vacuum, born in the quiet and the weightlessness. This is the profound advantage of space-based manufacturing. It allows us to think and build at the true scale of the cosmos, creating not just machines, but entirely new forms of matter and architecture, designed from the atom up for a life among the stars. So we have the means to produce vast quantities of specialized materials in space. But what exactly are we building? The fundamental unit of the entire Dyson swarm is not a factory or a mining rig, but a single, purpose-built solar collector satellite. Think of it as a worker bee in a cosmic hive, each one a self-contained power station designed for a solitary, vital task, capturing sunlight and sending the energy where it is needed. Its design is a masterclass in efficiency, born from the unique constraints of space. It must be incredibly lightweight to minimize construction costs, yet robust enough to survive decades of micrometeoroid impacts and solar radiation. It must generate and manage immense power, and it must have a way to deliver that power across the void. The most likely form is a vast, kilometers-wide structure, but one that is almost ghostly in its thinness. One elegant design uses thin film photovoltaics, the same refined silicon sheets produced by our orbital factories. These ultra-light, flexible panels would be unfurled in space, supported by a delicate lattice of carbon fiber or metal struts printed in intricate, weight-saving patterns. They would passively convert sunlight directly into electricity. An alternative and potentially more efficient design is a solar thermal system. Here, the satellite would use a gigantic parabolic mirror, perhaps spun from molten glass, to focus sunlight onto a central receiver. That concentrated heat, rather than being turned directly into electricity, would drive a Stirling engine. This is a beautifully simple closed-cycle engine where heated gas expands and cools, driving a piston to generate power with remarkable efficiency and few moving parts. Whether photovoltaic or thermal, the satellite now has a raw stream of power. This is where its brain comes in. Integrated power management systems, sophisticated electronics hardened against radiation, must condition this electricity, converting it to a stable, usable form and storing any excess in advanced batteries or perhaps by spinning up flywheels. But power trapped on an isolated satellite is useless. The energy must be transmitted. This leads to one of the most iconic aspects of the design, the transmitter. To send this power across millions of kilometers without wires, we would likely use either microwaves or lasers. A microwave system would involve a large phased array antenna, carefully directing a low-intensity beam of radio waves toward a receiving station or rectenna on a distant world or spacecraft. A laser system would be more precise, using a focused beam of light, but requiring even more exact aiming. Both methods convert the satellite's electricity into a coherent beam that can travel through space with minimal loss. Finally, this delicate, kilometers-wide instrument cannot simply be placed and forgotten. It needs station-keeping propulsion, tiny, precise thrusters, often just small ion drives or cold gas jets, that make minute adjustments over years. They counteract the subtle but relentless pressure of sunlight itself, which would slowly push the satellite off course and maintain its precise position in the orbital ballet to avoid collisions. The ultimate goal of our exponential space factories is the mass production of these units, not custom-built masterpieces, but identical, modular, and reliable satellites, rolling off the assembly line by the thousands, then the millions. Each one is a single thread in an emerging tapestry, a point of light that, when joined by countless others, begins to weave a net around a star. The exponential power of self-replicating automation is the only engine capable of building a structure of stellar scale. We call this theoretical concept a von Neumann probe, a machine designed with one ultimate purpose: to create a perfect copy of itself using only the raw materials it finds in its environment. For our Dyson swarm, this is not a far future speculation. It is an absolute logistical necessity. The numbers make this brutally clear. Even with our most optimistic projections, building and launching millions of collector satellites from Earth would take millennia and consume the entire economic output of our planet for centuries. The chain of supply would be impossibly long, fragile, and slow. To cross the chasm from a prototype to a true swarm, we must design a system that can grow on its own, turning the resources of the solar system into more machines that can gather more resources in a virtuous, accelerating cycle. The heart of this system is the seed factory we introduced earlier, but now we must understand its true, transformative nature. This initial package, launched from Earth, would be the most complex and valuable payload in human history. It would not be a general-purpose factory, but a meticulously designed starter kit containing a core set of versatile machines. Think of a high-precision, three-dimensional metal printer capable of crafting its own replacement parts. A robotic assembly arm with the dexterity to wire circuits and bolt frames together. A solar panel fabricator to create its own power supply, and a sophisticated computer system housing the blueprints for every component of itself and for the eventual power satellites it will build. Its first mission upon reaching the first captured asteroid is one of survival and replication. Using the refined metals and silicon we discussed, it would not immediately start producing solar collectors. Instead, it would painstakingly manufacture the components for a second 3D printer, then a second assembly arm. It would use its own solar panels to power this slow, deliberate act of creation. Once the duplicate set of core machines is complete, the robotic arms would assist in assembling them into a new, independent factory unit. This is the pivotal moment, the genesis. From one factory, we now have two. This is where the exponential curve begins. Each new factory, now operating with the same instructions and the same access to asteroid material, repeats the process. 2 factories become 4, 4 become 8. The growth is not linear, it is geometric, leaping forward with each generation. Within a surprisingly short span of time, perhaps just a few decades, a single seed could blossom into a network of thousands of autonomous production hubs, scattered across the resource-rich asteroids of the inner solar system. This changes everything about the project's economics and timeline. The initial cost and effort are concentrated in that first, fragile seed. Every subsequent factory and every millionth solar collector satellite costs essentially nothing in terms of Earth-based resources, only the time and energy harvested from the sun itself. The human role shifts dramatically from hands-on construction managers to architects and supervisors. Our job becomes one of high-level oversight, setting broad production goals, uploading updated designs for more efficient collector satellites, and monitoring the overall health and coordination of the growing machine ecology. We are planting a forest of industry, not by placing every tree, but by carefully designing the first seed and ensuring it has the right conditions to grow. This vision of self-replicating automation is the key that unlocks the solar system, transforming an impossible construction project into a patient, inevitable process of cosmic growth. This entire vision hinges on a single, seemingly impossible requirement. We need colossal amounts of energy to build the very machines designed to capture colossal amounts of energy. It is the ultimate cosmic catch-22. You cannot build a Dyson swarm without the power of a Dyson swarm to run the factories. This is the bootstrapping problem, the first and most critical hurdle any real project would face. To climb this mountain, we must start with the tiniest, most reliable footholds of power we can bring with us from Earth. The initial energy source for our seed factory cannot rely on the infrastructure it is meant to create. It must be self-contained, robust, and capable of operating in the deep darkness far from the consistent, full-strength sunlight of an ideal solar orbit. For this foundational role, we would almost certainly turn to nuclear fission. A compact, high-output fission reactor, delivered from Earth as part of that precious seed payload, would be the beating mechanical heart of the entire operation's first phase. It would provide steady, reliable power regardless of the asteroid's rotation or its distance from the Sun, running the initial three-dimensional printers, the computers, and the life support systems for any early human overseers. This delivered reactor is the indispensable spark that ignites the entire industrial chain, but fission alone cannot scale to meet the demands of exponential growth. Its fuel must be shipped from Earth, a costly and limiting tether. To truly break free, we must immediately begin harnessing the local power source, the Sun itself, even from our less-than-ideal starting position. This is where elegantly simple technology makes its grand entrance. Among the first products manufactured by the seed factory, even before it replicates itself, would be vast sheets of metallized polymer foil. This is not complex machinery. It is essentially highly reflective, ultra-thin film, like a space-age emergency blanket but kilometers wide. These foils would be mechanically unfurled and carefully positioned to act as primitive solar concentrators, giant mirrors focusing raw sunlight onto a central point. That concentrated heat, easily reaching thousands of degrees, becomes our first locally sourced industrial tool. These solar furnaces would power the next critical step, the purification processes we discussed earlier, melting regolith and driving electrolysis to produce the first batches of pure metal and silicon from the asteroid. They provide the thermal energy for baking out water and volatiles. This combination, the steady, reliable pulse of fission and the immense, focused heat of concentrated sunlight, forms the Bootstrap power package. It allows the seed factory to produce its first generation of true solar power collectors. These initial collectors would be crude by later standards, perhaps simple photovoltaic arrays or basic solar thermal engines, but their function is monumental. As soon as they come online, they begin feeding electricity directly back into the growing factory complex. Each new watt they generate is a watt that doesn't have to come from the limited fission reactor. This is the pivotal transition. The system begins to nourish itself. The power from collector generation 1 is used to build the machines that make collector generation 2, which are more efficient and produce even more power. That increased energy budget then accelerates the replication of factories and the scale of mining operations. A positive feedback loop is born. The bootstrap phase is the hardest and slowest part of the entire endeavor, a period of painstaking investment where returns seem negligible. But once that loop closes, once the system's own energy output surpasses the input from its Earth-delivered reactor, the project achieves energy independence. The nuclear heart can be idled, its fuel preserved for emergencies. From that moment forward, growth is fueled by the Sun, using the very materials of the asteroids to capture more of the Sun's energy to process more asteroids. The bootstrap is the difficult, crucial act of lifting ourselves by our own cosmic bootstraps, creating the first whisper of the roar to come. The positive feedback loop of energy and industry is now established, a self-sustaining pulse of creation. But this growth cannot be chaotic. As the first few thousand collector satellites roll off the assembly lines, a new and far more delicate challenge emerges, one of cosmic choreography. We are no longer just builders, we are city planners for a metropolis that will span an entire star system. And our primary concern is not architecture, but emptiness, the vast spaces between our creations. The fundamental rule of this new city is simple, yet its implementation is breathtakingly complex. Nothing can ever collide. A single impact between two satellites traveling at orbital speeds would create a catastrophic cloud of shrapnel, potentially triggering a chain reaction that could render entire orbital highways unusable. To prevent this, we must abandon the idea of a single, neat ring of satellites, like Saturn's rings around the Sun. That arrangement would be a disaster. Satellites would constantly cast shadows on each other, eclipsing their power collection, and their orbits would inevitably intersect. Instead, we must think in 3 dimensions, constructing a dynamic, multi-layered shell. The swarm will occupy a vast volume of space, likely centered around the Sun at a distance similar to Earth's orbit, where sunlight is strong and stable. Within this spherical shell, we will distribute our satellites across a carefully designed spectrum of orbital planes and altitudes. Some will orbit in the plane of the solar system, the ecliptic. Others will be placed in orbits tilted at various angles, creating a lattice of paths that, if viewed from afar, would resemble a finely meshed globe. The spacing between individual orbital paths is calculated with extreme precision, ensuring that even as satellites complete their years-long journeys around the Sun, their paths never come close to crossing. It is less like cars on a single highway and more like layers of independently moving glass spheres, each etched with its own unique set of rings, all nested within one another without touching. But even this intricate ballet has a limitation. Every traditional orbit requires the satellite to be in constant motion, which means it will eventually drift behind the Sun relative to a fixed point like Earth, creating a transmission blackout. For critical infrastructure that requires a constant, unwavering energy beam, we need a satellite that can hold its position, not in orbit but in a fixed location. This brings us to a concept that seems to defy orbital mechanics, the statite. A statite is a satellite that does not orbit at all, it hovers. It accomplishes this feat not with rockets, but with a solar sail, an immense reflective sheet. The constant pressure of sunlight pushing against the sail can be perfectly balanced against the Sun's gravitational pull. By carefully angling the sail, a statite can maintain a stationary position relative to the Sun and a receiving station, acting as a permanent power relay in the sky. These would likely be reserved for key logistical nodes like the Lagrange points, creating stable hubs in the flowing river of orbital traffic. Managing this system, where billions of independent units are in motion, is a task far beyond any centralized human control. This is where autonomous navigation becomes the silent, invisible governor of the swarm. Each satellite is endowed with a sophisticated suite of sensors, a simple artificial intelligence, and its own micro-propulsion system. It constantly monitors its own position with stellar navigation and communicates with its nearest neighbors, not with a central command, but in a distributed network. If its sensors detect another satellite drifting slightly too close, its onboard computer calculates a minuscule corrective burn, a puff of cold gas or a brief pulse from an ion drive, to adjust its path and restore the safe buffer zone. These corrections are tiny, constant, and automated, a ceaseless whisper of thrust maintaining harmony across billions of kilometers. The swarm manages itself, a vast, intelligent organism whose collective behavior is stability, its simple goal to ensure every member has enough space and sunlight to fulfill its purpose. This is the invisible masterpiece of engineering, the flawless, silent code that turns a cloud of machinery into a coherent, enduring civilization. The silent symphony of the swarm is now complete, a cloud of machines harvesting sunlight on an unimaginable scale. But this energy is trapped, a brilliant potential humming in the vacuum. For the swarm to fulfill its purpose, for it to power civilizations and propel ships between worlds, we must solve the final, elegant puzzle of logistics: how to move this power across the emptiness of space without a single wire. This is the realm of beamed energy, a technology that transforms electricity into a directed stream of light or radio waves, sending it precisely where it is needed. The customers for this cosmic utility are diverse, a growing interplanetary civilization. It could be a research outpost on Mars, thirsty for power during a global dust storm. It could be a fleet of robotic freighters hauling ice from the rings of Saturn, needing a boost to shorten their journey. Or, on the grandest scale, it could be Earth itself, receiving a continuous, clean supplement to its planetary energy grid. To service these clients, the swarm would employ two primary methods, each with its own profound advantages and challenges. The first is microwave transmission. Think of a satellite not with a solar panel, but with a colossal, dish-shaped structure, a phased array transmitter composed of millions of small antenna elements. By carefully controlling the timing of the microwaves emitted from each tiny element, the entire array can shape and steer a coherent, low-intensity beam with incredible precision, aiming it at a receiving station or rectenna millions of kilometers away. This beam is not a destructive ray, it is more like a very focused radio broadcast. The rectenna on the ground is its counterpart, a vast field of simple wire mesh designed to resonate at the specific microwave frequency. As the beam strikes this mesh, it induces a tiny electrical current in each wire, and the combined effect across the entire field is transformed back into usable grid electricity. Microwave beams can penetrate clouds and light rain with minimal loss, making them reliable for planetary delivery. The second method is laser transmission. Here, the satellite uses powerful, specially tuned lasers to create an extremely tight beam of infrared or visible light. The advantage is breathtaking focus. A laser beam can be aimed with pinpoint accuracy at a much smaller receiver, perhaps a collector on a distant spacecraft only meters across. This makes it ideal for powering specific, mobile targets across the solar system. However, laser light is easily scattered or absorbed by atmospheric conditions like clouds or dust, so for beaming to a planetary surface, it requires exceptionally clear skies and possibly a network of relay mirrors in high orbit. The engineering behind these transmitters is a marvel in itself. A single phased array for microwaves might need to be tens of kilometers across to keep the beam diffuse and safe by the time it reaches a planet, ensuring its energy is spread over a wide area rather than a single hotspot. Building structures of this scale is only possible with the microgravity manufacturing we have already mastered, spinning gossamer thin reflective films and printing intricate antenna lattices. On the receiving end, the infrastructure is equally monumental. A rectenna for Earth might need to cover hundreds of square kilometers of desert or ocean surface, a passive, low-maintenance grid of wires that doubles as grazing land or is mounted on floating platforms. This scale naturally raises vital questions of public safety. The idea of a beam from space powerful enough to energize cities sounds understandably concerning. But the engineering principles are deliberately designed for safety. Both microwave and laser systems for planetary delivery operate at an intensity far below harmful levels at the ground. The microwave beam, by the time it reaches the rectenna field, would be no more concentrated than midday sunlight. The systems would include multiple, redundant layers of safety, from precise targeting lasers that constantly verify the receiver's position to automatic shut-off protocols if the beam were to ever drift off course by even a fraction of a degree. The goal is not a weapon but a utility as reliable and benign as a lighthouse guiding ships with its light, not burning them. This final act of transmission completes the loop, turning the abstract concept of stellar energy into a tangible current flowing into homes, factories, and engines across the solar system. The swarm is no longer just a collector, it has become a power company for an entire civilization, its product delivered on a beam of light. All the theory and grand design must now condense into a single, fragile point of light. The first true act of construction begins not with a fleet but with a single, deliberate mission, a proof of concept on a cosmic scale. This is Phase 1, the creation of the pilot facility. Its objective is deceptively simple: to take the entire chain of technologies we have envisioned, from capture to finished product, and prove they can function together as a unified system in the harsh reality of deep space. The target is not a massive, resource-rich worldlet, but a carefully chosen small near-Earth asteroid, perhaps only a few hundred meters across. It is selected for its stable, accessible orbit and its manageable size, a celestial testbed rather than a primary resource. The payload launched from Earth is the culmination of centuries of engineering, the seed factory. It is a compact, heavily shielded vessel containing the core of our future industry, the 3D printers, the robotic arms, the computers with the stored blueprints, and that crucial, compact fission reactor to provide the initial, unwavering spark of power. After a journey lasting months or years, it arrives not with a dramatic impact but with a gentle, precise rendezvous, matching the asteroid's slow tumble through the void. The capture process begins immediately, not to move the mountain but to anchor to it. Harpoons fire, embedding tethers into the rocky surface. Robotic climbers traverse these lines, bolting down foundational platforms and securing the entire factory complex to the asteroid itself, turning this drifting rock into a fixed worksite. Then the bootstrap power system awakens. The fission reactor hums to life, providing the electricity for the first, painstaking steps. Simple reflectors, manufactured from foil brought from Earth, are unfurled to concentrate sunlight, creating the first solar furnace. Mining commences with cautious, deliberate movements. A robotic arm powered by the reactor extends a grinding tool to pulverize a small patch of the asteroid's surface. The resulting regolith is fed into a sealed processing chamber where concentrated sunlight heats it to extreme temperatures. Volatiles bake off and are captured, water vapor condensing into a first precious reservoir. The remaining material undergoes electrolysis, with electricity from the reactor splitting the melted rock, yielding bubbles of oxygen and a small, gleaming pool of pure iron. This first batch of material is monumental. It is not yet used to build a power satellite. It is used to build more tools. That purified iron powder is fed into the 3D printer. Slowly, layer by layer, it fabricates a more robust grinding head for the mining arm. It prints a more efficient heat exchanger for the processing unit. It creates additional structural braces to reinforce the factory. The system is literally building its own upgraded body from the bones of its new home. Only after this cycle of self-improvement is established does it turn to its primary goal. Using refined silicon and more metal, it manufactures the components for the very first prototype collector satellite. These parts are not sleek and optimized. They are robust, over-engineered, and packed with sensors. A simple photovoltaic panel is printed and mounted on a lightweight truss. A small ion drive and navigation system are assembled. In a clean tent inflated on the asteroid's surface, robotic arms meticulously bolt and wire everything together. After months of work, the first complete unit is released. It drifts free of the asteroid, its own small solar panels deploying. It powers up, runs diagnostics, and fires its thrusters to move into a simple, nearby orbit. A few weeks later, a second, slightly improved prototype follows. These first units are not designed for efficiency, but for data. They are instrumented to report every strain, every temperature fluctuation, every micrometeoroid impact. They test the power beaming systems, sending a faint, targeted microwave signal back to a small rectenna installed on the factory itself. The trickle of power they return is symbolic, perhaps just enough to run a single computer console, but its meaning is universe-shaking. For the first time in history, a functioning piece of a Dyson swarm has been built entirely from extraterrestrial materials, using energy harvested on site. The pilot facility has validated the core loop. It has turned inanimate rock into a machine that captures starlight. The phase is a resounding success not because of the power it produces, but because it proves the entire audacious concept is not just possible, but practical, providing the hard data and refined processes needed to greenlight the next explosive phase of growth. Phase 1 has closed its loop, proving the fundamental principle. A tiny trickle of power now flows from a machine built of asteroid rock, a whisper that contains the blueprint for a roar. With the pilot facility's data in hand, the project enters its most transformative stage, where linear progress gives way to an exponential explosion of capability. The single, anchored factory on its test asteroid initiates the sequence it was designed for, not just making collector satellites, but meticulously building a copy of its own core machinery. This act of mechanical reproduction is slow and deliberate, a ballet of robotic arms assembling a second 3D printer, a second set of refining chambers from the refined materials of its home. Once complete, this duplicate factory kit is not kept in place. It is loaded onto a simple, efficient transport powered by ion drives and fed by asteroid propellant and dispatched across the void. Its destination is a new asteroid already identified and characterized by our survey network, one with a complementary composition, perhaps rich in the carbon or rare metals the first site lacked. This is the moment of dispersal, the seeding of industry across the solar system. The original pilot facility becomes Node Alpha, the first point in what will become a vast decentralized network. Each new node, upon establishing itself, repeats the process. Node Beta builds and sends a seed to an asteroid in a different orbital plane, creating Node Gamma. Gamma, in turn, seeds Delta and Epsilon. Like dandelion seeds carried on a solar wind, these self-replicating factories spread, not randomly, but along a pre-calculated expansion map, claiming resource-rich asteroids as stepping stones. The growth is no longer additive, it is geometric. 1 becomes 2, 2 become 4, 4 become 8. This is where a kind of Moore's law for physical manufacturing emerges. Just as computer chips doubled in complexity every 2 years, the production capacity of this industrial network could double every few years, constrained not by miniaturization, but by the speed of replication and the availability of raw materials. In the beginning, doubling a tiny output seems insignificant, but as the base grows, each doubling represents a staggering leap. It might take a decade to go from 1 factory to 64. But the next doubling to 128 happens in the same time frame, and those 128 factories collectively produce more in a month than the original pilot did in its entire first year. This is the snowball effect, a slow roll at the top of the hill that becomes an avalanche. The production of collector satellites accelerates from a few prototypes per year to hundreds, then thousands, then millions per year. We can project this growth over the long arc of centuries. In the first 50 years, the effort might seem almost quaint, capturing a minuscule fraction of the sun's total output, perhaps just 1/1,000,000th of 1%. But that energy is entirely reinvested into building more capacity. By the end of the first century, the swarm might capture a measurable percentage, enough to power all of human civilization thousands of times over. After 2 centuries of relentless, automated growth, the network of factories and collectors could be capturing a significant fraction of the sunlight that falls within Earth's orbital distance. The curve is not endless, of course. It will eventually saturate as the most easily accessible asteroids are consumed and the optimal orbital space fills. But by that point, the transformation is complete. The project transitions from a frantic, exponential build phase into a steady state of maintenance and incremental improvement, a mature technological ecology humming around its star. This scaling is not magic. It is the inevitable outcome of a simple, powerful rule applied on a cosmic stage, a rule of replication where every successful unit is programmed to create 2 more. This exponential growth creates a logistical challenge of its own, a kind of cosmic supply chain management on an interstellar scale. With factories now multiplying across the inner solar system, we can no longer treat every asteroid as a generic rock. Each one is a specialized package of elements, and the swarm's health depends on routing these resources with intelligent precision. An intricate network of autonomous freighters, themselves products of the orbital factories, begins to hum with activity. Their task is simple in concept but vast in execution: to match supply with demand across millions of kilometers. A metallic M-type asteroid, rich in iron and nickel, is tagged not for general use but specifically for structural components. Its ore is processed into the beams, struts, and frames that form the skeletons of new power stations and factory modules. Meanwhile, a carbonaceous C-type asteroid, brimming with carbon compounds and water ice, is routed along a different pathway. Its volatiles are cracked into hydrogen and oxygen for rocket fuel and breathable air, while its carbon becomes the basis for advanced polymers, radiation shielding, and the semiconductors at the heart of every computer. Rare, stony S-types might be prioritized for their precise blends of silicon and trace metals, essential for high-efficiency solar cells and advanced electronics. This is not a haphazard mining operation. It is a circulatory system with different celestial bodies acting as specialized organs, feeding specific materials into the growing body of the swarm. But a civilization that only consumes is not a civilization built to last. As the swarm matures, a new principle must take root: the imperative of recycling. Even the most robust collector satellite has a finite lifespan, worn down over centuries by relentless micrometeoroid pitting and the degrading effects of solar radiation. In a traditional model, these dead units would become hazardous space junk, drifting forever as silent, useless monuments. In our intelligent swarm, they become the most valuable resource of all: a concentrated depot of pre-refined materials already in orbit. The concept of a closed-loop material economy emerges. Decommissioned satellites are not abandoned. Instead, specialized tenders, perhaps little more than robotic tugs with simple processing arms, are dispatched to retrieve them. These units are guided back to the nearest factory node, where they are carefully disassembled. Their solar panels are stripped for silicon and glass. Their structural frames are melted down and purified once more. Their electronics are mined for rare earth elements and precious metals. Every gram is recovered and fed back into the manufacturing stream. This creates a beautiful and efficient cycle. The need for fresh asteroid capture never disappears, as the swarm will always expand and require new material, but the demand slows dramatically. The system begins to sustain itself, using its own worn-out parts as feedstock for its new growth. It minimizes waste in an environment where waste is not just litter, but a navigational hazard and a lost investment. This closed loop transforms the swarm from a simple consumer of asteroids into a sophisticated, self-renewing ecosystem. It learns to heal its own wounds and rebuild its own aging components, taking a crucial step from being a constructed thing toward becoming a living, enduring entity. A civilization powered by its own star would not be one without people. While the swarm grows through the tireless work of self-replicating machines, humanity's role undergoes a profound and necessary evolution, shifting from the hands that turn the wrench to the minds that guide the symphony. We move from being the primary labor force to becoming supervisors, architects, and philosophers for an automated ecosystem of staggering complexity. Our work becomes less about physical construction and more about high-level programming, system design, and the delicate art of maintaining harmony across billions of autonomous units. Imagine a control center not on Earth, but nestled within the industrial zone itself. Here, teams of engineers monitor vast holographic displays that map the entire swarm in real time, not to control every satellite, but to watch for emergent patterns, subtle drifts in collective behavior that might indicate a need for a software update or a recalibration of navigational protocols. Their task is to write the rules of the game, the elegant algorithms that allow the machines to manage themselves, and then to trust those rules enough to let them work. This requires a new kind of engineering mindset, one focused on resilience, adaptability, and the long-term health of a system that will outlive its creators by centuries. Beyond the pure mechanics of the swarm, an even more complex human system must emerge to manage its output. The distribution of nearly limitless energy creates profound economic and political questions. Who decides where the power beams are pointed? How is this new abundance allocated among nations, corporations, or fledgling colonies on Mars and the moons of Jupiter? The role of diplomats, economists, and ethicists becomes as critical as that of the orbital mechanic, tasked with building the social frameworks to ensure this cosmic utility benefits all of humanity, preventing new forms of scarcity or conflict from arising in an age of plenty. For the individuals and families who call this industrial frontier home, life would unfold not on planetary surfaces, but within immense, self-contained habitats orbiting alongside the factories. The most plausible design is the O'Neill cylinder, a vision from the last century made real by the manufacturing prowess of the swarm itself. Picture two vast cylinders, each perhaps 20 miles long and 5 miles in diameter, rotating in opposite directions to provide stable, Earth-like gravity along their inner walls. Their surfaces are sculpted into valleys, rivers, and towns, illuminated by massive, adjustable mirrors that reflect sunlight in a steady 24-hour cycle. The air smells of soil and growing things, not machinery, as entire ecosystems thrive under a transparent ceiling that shows a streaming tapestry of stars and the graceful movement of collector satellites. These are not sterile space stations, but verdant, vibrant communities where the engineers who oversee the swarm live, raise families, and look out their windows at the very civilization they are stewarding. In this future, humanity does not become obsolete, we become curators. Our purpose shifts from struggling against scarcity to mastering the responsibilities of abundance, from building machines to nurturing the delicate balance of a system that powers our dreams. The ultimate success of the Dyson swarm is measured not in terawatts captured, but in the quality of civilization it enables, a testament to a species that learned to build with the stars, and then learned what to build with the time and energy that freedom provided. The true power of a Dyson swarm lies not in what it collects, but in what it makes possible. Once this foundational utility is in place, humming with energy and industrial might, it ceases to be an end in itself and becomes the ultimate platform, the springboard for a civilization that can reshape its entire solar neighborhood. This vast network of power and production enables projects that would otherwise be pure fantasy, turning the swarm into the backbone of a truly spacefaring society. Consider the dream of large-scale space habitats, like the O'Neill cylinders we mentioned. Building such enormous, Earth-like environments requires staggering amounts of structural material, life support systems, and interior landscapes. With the swarm's factories already processing asteroids by the gigaton, the raw materials become trivial. More importantly, the swarm provides the immense, continuous energy needed to process those materials, spin the cylinders for gravity, and illuminate the interior with vast, adjustable mirrors. The swarm doesn't just make these habitats possible, it makes them practical, turning them from isolated experiments into entire new branches of humanity with their own cultures and economies. This energy abundance also redefines the economics of travel. Today, every journey beyond Earth orbit is a careful calculus of mass and fuel, a slow, patient coasting along gravitational highways. With the swarm, we could establish a network of beamed power stations across the solar system. A spacecraft no longer needs to carry all its reaction mass for the entire journey. Instead, it could deploy a lightweight solar sail or a microwave receiver. As it travels, it catches a tailored energy beam from the nearest swarm transmitter, using that power to run a high-efficiency ion drive or even to heat onboard propellant to incredible temperatures. This turns interplanetary travel from a rare, years-long expedition into something more akin to a high-speed rail network. A trip to Mars could be measured in weeks, not months. Missions to the outer planets could be undertaken routinely, opening the icy moons of Jupiter and Saturn for resource gathering and exploration. The swarm becomes the fueling station for the entire solar system. Its energy beams the invisible highways upon which our ships sail. On a planetary scale, the swarm's precision offers tools for planetary stewardship. The same technology that focuses sunlight onto power receivers could, in principle, be adapted for climate engineering. A constellation of thin, adjustable mirrors positioned at a stable point between Earth and the Sun could cast a finely tuned, diffuse shadow over our planet. This wouldn't be a crude blotting out of the Sun, but a subtle modulation, reducing a precise fraction of incoming solar radiation to help mitigate global warming. The energy and manufacturing capacity to build and maintain such a sunshade megastructure could only come from an industrial base like the Dyson swarm. It represents a profound responsibility, of course, one requiring global consensus and exquisite control, but it showcases the level of planetary influence such infrastructure grants. Furthermore, the swarm provides the perfect foundation for science on a cosmic scale. By constructing telescopes and sensor arrays directly onto the swarm's platforms, we could create an astronomical observatory of unimaginable size and stability. Freed from the distortion of Earth's atmosphere and the vibrations of a planetary surface, these instruments could have lenses or mirrors measured in kilometers, not meters. They could peer into the atmospheres of distant exoplanets with stunning clarity, listen for the faintest gravitational waves, or look so deep into the infancy of the universe that the cosmic microwave background would resolve into intricate detail. The swarm's constant power supply means these instruments could operate continuously, gathering data for centuries, unlocking secrets of physics and cosmology we can barely glimpse today. In this light, the Dyson swarm transforms from a power plant into something far grander, the foundational infrastructure for a solar system-wide civilization. It is the electrical grid, the industrial supply chain, the transportation network, and the research institute, all woven into one dynamic, growing entity. It provides the energy surplus that frees humanity from scarcity and the industrial capacity to turn dreams into reality, whether those dreams are new homes among the stars, rapid journeys to distant worlds, careful stewardship of our home planet, or a deeper understanding of the cosmos itself. The swarm is the tool that allows a civilization to graduate from living on a planet to actively inhabiting its star system, shaping its environment not just for survival, but for a flourishing future limited only by imagination and wisdom. The grandest engineering project in history will ultimately be a political one. While the silent, automated factories replicate in the void, their work will be shaped by a more complex and unpredictable system, the competing interests of humanity itself. Constructing a Dyson swarm is not just a feat of physics and robotics. It is a profound exercise in governance, demanding a framework for cooperation on a scale we have never before achieved. The challenges are not in orbit, but in our own halls of power and boardrooms. Who owns the asteroids we redirect? Who has the right to occupy the most valuable orbital pathways around the Sun? How do we decide where the immense beams of energy are directed, and who pays for this cosmic utility? These questions require answers before the first seed factory is ever launched, for the rules we establish will determine whether this project unites our civilization or becomes its greatest source of division. The current legal framework for space, anchored by the Outer Space Treaty of 1967, is a foundation built for an era of exploration, not industrialization. It declares that no nation can claim sovereignty over celestial bodies, that space is the province of all humankind. This noble principle becomes incredibly complex when applied to the practical act of mining a specific asteroid. If a company or nation spends vast resources to capture and process an asteroid, do they own the materials they extract? Most interpretations of space law suggest yes. They possess the products of their labor, but they cannot claim the asteroid itself as territory. This creates a need for a new, transparent system of claims registration and resource rights, likely administered by a reformed or newly created international body. Without clear, universally recognized rules, the first movers could trigger disputes that stifle investment and breed conflict before the project even begins. Orbital real estate presents another delicate puzzle. Just as geostationary slots above Earth are carefully allocated to prevent satellite collisions, the solar orbits for our swarm must be managed with exquisite care. The most efficient and stable orbits, particularly those in the same plane as Earth, will be in incredibly high demand. A free-for-all could lead to dangerous congestion and catastrophic accidents, turning the swarm into a minefield. This necessitates a supranational traffic authority, an entity with the technical mandate and political legitimacy to assign orbital pathways, enforce safety regulations, and decommission defunct units. Its authority would need to be absolute in its domain, respected by all participating entities, to maintain the long-term stability of the entire system. Then comes the question of the energy itself. What is the economic model for a utility that can power worlds? One vision is a public trust, a solar system-wide public utility operated for the benefit of all humanity, perhaps managed by a democratic consortium of nations and colonies. Its goal would be equitable access, beaming power to developing regions on Earth or struggling outposts on Mars as a form of common infrastructure, much like the Internet's foundational protocols. An alternative model is a competitive market. In this scenario, different consortia or corporations could operate their own segments of the swarm, selling beamed power to customers, planetary governments, mining operations, spacecraft in an open marketplace. This could drive innovation and efficiency through competition, but it also risks creating energy haves and have-nots, where access is determined by wealth rather than need. The reality would likely be a hybrid, a regulated market with a guaranteed basic energy allocation for essential civilizational needs, ensuring no community is left in the dark. The shadow over all these discussions is the risk of conflict. Control over the swarm's output would represent the greatest concentration of economic and strategic power in human history. The ability to grant or withhold energy could become a tool of immense political pressure. Safeguards would need to be engineered into the system's very architecture. This could include technical protocols that prevent any single entity from controlling a decisive majority of the transmitters, or legal structures that treat the core power beaming infrastructure as a neutral common carrier, obligated to serve all clients without discrimination. The goal must be to design a system where the cost of seizing control is astronomically higher than the benefits of cooperation, weaving stability into its political and technical DNA. Navigating these hurdles will demand as much ingenuity as the engineering itself, for the ultimate test of a Type II civilization may not be its mastery of matter and energy, but its mastery of its own nature. Such a project cannot be measured in fiscal years or political terms. Its true timeline unfolds across centuries, a patient cadence that aligns with the orbital rhythms of the solar system itself. This is not a task for a single generation, but for a civilization that learns to think in lineages, viewing its work as a gift to descendants it will never meet. Yet, when placed against the lifespan of stars or the age of our galaxy, this grand construction is astonishingly brief, a fleeting moment of focused ambition in the deep time of the cosmos. We can chart this journey in distinct eras, each with its own character and milestones. The 21st century is our preparatory phase, the time of laying the groundwork. Right now, we are in the midst of it. This era is defined not by construction, but by discovery and demonstration. Robotic probes are already visiting asteroids, sampling their surfaces, and testing our ability to interact with them. Projects like the NEO Surveyor telescope will soon begin their systematic census, turning unknown dots of light into a mapped inventory of resources. In laboratories and test facilities on Earth, engineers are refining the core technologies, advancing the efficiency of ion drives, perfecting three-dimensional printing in microgravity simulators, and pushing the limits of autonomous robotics. This century is about answering the critical questions, proving we can reliably extract water from regolith, manufacture a simple component in space, and navigate the complex legal frameworks for resource use. It is a time of prototypes and policy, setting the stage for the first real action. The 22nd century becomes the Bootstrap Era, where theory meets the unforgiving reality of deep space. This is when the first seed factory, the culmination of a century's preparation, makes its journey to a carefully selected target. The 22nd century is defined by its slowness and its profound symbolic weight. For decades, the pilot facility will work in isolation, a tiny island of industry on a dark rock, methodically proving the closed loop we described. It will capture its first asteroid, process its first grams of metal, and build its first functional, if rudimentary, power collectors. The energy output at this stage is negligible, perhaps just enough to power the facility itself and beam a symbolic trickle back to a waiting receiver at a lunar outpost. The true product of this century is not energy but certainty. It is the hard-won data, the refined processes, and the confidence that the fundamental principle works. Toward the end of this era, we would witness the first act of replication, as the initial node successfully builds and dispatches a second factory to a new asteroid. This single event, the creation of a second independent node, is the pivot point of history, the moment the project's growth curve begins its slow, inevitable turn upward from linear to exponential. With replication proven, the 23rd century erupts into the exponential build-out. This era is defined by acceleration, a snowball effect gaining mass and speed. The two factories become 4, then 16, then hundreds. The swarm's population of power collectors climbs from thousands to millions to billions. Vast, specialized freighters ply routes between resource asteroids and growing industrial hubs. Orbital space around the Sun begins to visibly fill with the glitter of carefully spaced satellites, a fine haze detectable by powerful telescopes on Earth. The energy output climbs from a tiny fraction of a percent to a measurable portion of the sunlight falling within Earth's orbit. This is the century where the swarm transitions from a spectacular experiment to the dominant feature of human civilization's infrastructure. It powers the construction of the first large-scale O'Neill cylinders, fuels rapid transit across the inner solar system, and begins to supply a major share of Earth's own energy grid through precise, safe power beams. The pace of change becomes dizzying, with each passing decade bringing capabilities that would have seemed like magic to the engineers of the bootstrap phase. By the 24th century, the project enters its maturation phase. The frantic, exponential growth begins to level off as the most accessible resources are incorporated, and the optimal orbital space reaches a carefully managed capacity. The swarm is now a mature technological ecology, capturing a significant fraction of the Sun's total output. It operates in a steady state, with sophisticated recycling streams repurposing decommissioned satellites and automated tenders performing perpetual maintenance. The human role is fully that of stewards and beneficiaries, living within the habitats the swarm made possible and directing its output toward new cultural and scientific pursuits. This entire arc, from the first surveys to a functioning stellar civilization, spans roughly 300 to 400 years. It is a timeline that stretches beyond any individual life, demanding institutions and a culture capable of long-term commitment. Yet, in cosmic terms, it is the blink of an eye. Our sun will shine on for billions of years. To go from a species confined to its home planet to one that harnesses the power of its star in just a few centuries is not a slow crawl. It is a metamorphosis of breathtaking speed, a testament to what becomes possible when a civilization aligns its purpose across generations. The sheer scale of this centuries-long endeavor reveals a deeper truth. It cannot be built with the tools we have today. The vision of self-replicating factories and cosmic power grids rests upon a foundation of technologies that are still in their infancy, each one a monumental challenge that must be solved not as an end, but as a means to a greater whole. The journey to harness a star is, in reality, a catalyst that would force breakthroughs across every field of human knowledge, creating a wave of innovation with profound benefits right here on Earth. The first prerequisite is a leap in robotics and automation. The machines that will anchor themselves to asteroids, operate refineries in hard vacuum, and assemble delicate components cannot be remotely controlled from Earth with a 20-minute communications delay. They must possess a high degree of situational awareness and dexterous autonomy. We need robots that can perceive a chaotic, dusty environment, diagnose a malfunctioning grinder, and execute complex repairs with minimal human oversight. This goes far beyond today's industrial arms. It demands a new class of resilient, multi-purpose machines capable of surviving decades of radiation and extreme temperature swings while performing tasks as varied as welding a beam and threading a fiber optic cable. Their intelligence is the next critical pillar, a form of artificial general intelligence, or a GI. This is not the specialized software that plays chess or recognizes faces, but a broader, more adaptable form of machine reasoning. A GI overseer at a factory node would need to manage thousands of simultaneous processes, from inventory levels of metal powder to the health of its own robotic workforce. It would plan complex logistical chains, rerouting freighters around solar storms, or redesigning a component on the fly when a material shipment is delayed. It would be the ultimate project manager, capable of creative problem solving in an environment where no human can directly intervene. The development of such a system, safe, reliable, and aligned with human goals, is perhaps the single greatest technical and ethical hurdle of the entire project. Propulsion is another linchpin. Moving mountains across the solar system cannot rely on chemical rockets. Their thirst for fuel is insatiable. We need propulsion systems of incredible efficiency, engines that can run for years on just kilograms of propellant. The ion drives we have today are a promising start, but they must be scaled up by orders of magnitude in both thrust and durability. We may see the maturation of nuclear thermal or nuclear electric propulsion, using compact fission reactors to heat propellant to extreme temperatures or generate vast amounts of electricity for even more powerful ion arrays. Some designs even point toward fusion rockets, where the power of a miniature star provides the thrust to move celestial bodies. The mastery of sustained, high-efficiency thrust in space is what turns a multi-decade asteroid capture into a manageable operation of just a few years. And for the bootstrap power problem, the dream technology is clear: compact fusion. A reliable, net-positive fusion reactor that could be shipped from Earth would provide that initial spark of power with far greater density and longevity than any fission system, jump-starting the entire industrial chain with a cleaner, more abundant energy source. The pursuit of these technologies for the swarm would inevitably solve challenges for our own world. The advanced materials needed for reactors and engines that can withstand stellar conditions would lead to new superalloys and ceramics, revolutionizing everything from jet engines to power plant turbines. The relentless focus on closed-loop life support, where every drop of water and molecule of oxygen is reclaimed, would gift Earth with hyper-efficient systems for recycling waste and purifying water in the most resource-scarce regions. The medical research into sustaining human health in rotating habitats, combating bone density loss and radiation effects, would unlock new understanding for treating osteoporosis and cancer on Earth. The very act of trying to build a miniature, sustainable biosphere inside a space habitat would teach us invaluable lessons about managing our own planetary ecosystem, creating models of environmental balance we could apply to heal forests, oceans, and atmospheres. In this way, the Dyson swarm is more than a destination. It is an engine for human progress, a grand challenge that pulls our entire technological civilization upward, leaving a trail of transformative spin-offs in its wake. Such immense power and autonomy cannot be contemplated without an equally sober assessment of what could go wrong. The scale of a Dyson swarm introduces failure modes that are themselves planetary in consequence, demanding that we design not just for success but for graceful failure. The most iconic risk is a runaway replication event, a macro-scale echo of the theoretical gray goo scenario. Imagine if the self-replication protocol in a factory node were corrupted, either by a software error, radiation-induced mutation in its code, or deliberate sabotage. Instead of building power collectors, it begins producing nothing but copies of its own flawed blueprint, ignoring resource limits or orbital assignments. These rogue factories could theoretically consume every available asteroid in their path, not for construction, but for mindless, exponential self-duplication, creating a wave of sterile industrial sprawl that blocks sunlight and resources from the rest of civilization. While the slow pace of physical replication makes this less an instant apocalypse and more a glacial tide, the outcome would be just as final, a solar system choked by its own mechanical progeny. Preventing this requires multiple, independent layers of control. Each factory's replication cycle would be governed by a hard-coded limit, a maximum number of generations, or a mandatory shutdown command after a set period, requiring a verified reset from an external authority. Its programming would be etched into radiation-hardened, non-rewritable core memory, separate from its operational software. Most importantly, the system would be designed with a built-in asymmetry. The factories would be brilliant at building power collectors, but deliberately inefficient at building the ultra-complex tools needed to build more factories, creating a natural bottleneck that human overseers control by regulating the flow of those specific components. The goal is to make runaway replication not just illegal but physically difficult and slow, giving stewards ample time to detect and quarantine any aberrant node. A more immediate and kinetic danger is a cascading collision within the swarm itself, a Kessler syndrome expanded to solar proportions. A single major impact, whether from an undetected natural meteoroid or a satellite malfunction, could generate a cloud of high-velocity debris. In the densely populated orbital shells, this shrapnel could strike neighboring satellites, creating more debris in a terrifying chain reaction. Within a matter of years, entire orbital pathways could become impassable fields of whirling metal, destroying billions of units and rendering that region of space around the Sun a permanent no-fly zone, effectively crippling the swarm's output and creating a lethal barrier for future travel. The defense here is a combination of extreme spacing, relentless surveillance, and autonomous avoidance. The orbital architecture we discussed, with its vast buffers between flight paths, is the first and best defense, making accidental collisions astronomically unlikely. Every satellite would be equipped with sensors to track nearby objects down to the size of a bolt, and its navigation system would be programmed to treat any object within 100 kilometers as an imminent threat, executing a gentle, pre-programmed evasion maneuver. Furthermore, the system would include dedicated Sentinel satellites, whose sole job is to map debris fields and coordinate slow, clean-up missions using magnetic nets or gentle laser nudges to deorbit fragments into the Sun. The swarm must be designed to be self-healing, capable of isolating and repairing damage before it can spread. The very feature that makes the swarm useful, its ability to beam concentrated energy across the solar system, also presents a profound security challenge. A power beam capable of energizing a city could, if misdirected or weaponized, become an instrument of unparalleled coercion or destruction. The safeguards against this must be both technical and political. Technically, the transmission systems would be designed with intrinsic safety features. The targeting would require a continuous, authenticated handshake signal from the intended receiver before the main beam could be activated, a system known as retrodirective targeting. If that signal were lost for even a millisecond, the beam would automatically and instantly shut down. The beam intensity for planetary delivery would also be inherently diffuse, its energy spread over a wide area to power a large rectina, making it impossible to focus into a destructive point. Politically, the control infrastructure for the most powerful transmitters would likely be distributed and require multi-party consensus, much like the launch codes for nuclear weapons. No single entity, corporate or national, could unilaterally decide where to aim a beam of that magnitude. The system would be architected so that its value as a peaceful utility vastly outweighs any potential utility as a weapon, making aggression an irrational choice for any actor dependent on its benefits. Finally, there is the risk of societal fragility. If human civilization reorganizes itself around the assumption of limitless, constant energy from the swarm, what happens if a portion of it fails? A prolonged, wide-scale outage could trigger collapse, as worlds and habitats have long since dismantled their old, redundant power grids. This creates a powerful imperative for resilience through decentralization and redundancy. The swarm would not be a single monolithic grid, but a network of semi-independent clusters, each capable of sustaining its local region if others go offline. Critical infrastructure on Earth and elsewhere would maintain backup fusion or fission power sources, not for daily use, but as an emergency buffer. Culturally, the knowledge of how to build and maintain the swarm's technology would be preserved and widely taught, not held by a priestly class of engineers. The system's greatest safeguard would be the distributed intelligence of its own caretakers and a society that understands its workings, ensuring that a single point of failure, whether mechanical or human, could never plunge civilization into darkness. These risks are not arguments against building, but blueprints for responsibility. They force us to integrate wisdom into our ambition, to build not just a machine, but a system that is stable, secure, and resilient by design, capable of enduring for millennia. The choice of our first celestial construction site will be one of the most consequential decisions in the project's history. We need a target that is not just scientifically interesting, but logistically forgiving, a celestial training ground where we can make our first mistakes without catastrophic cost. While the distant metallic world Psyche captures the imagination as a mountain of pure metal, its location in the main belt places it far beyond the practical reach of an early Bootstrap mission. Our first target must be a true near-Earth asteroid, one whose orbit brings it tantalizingly close, minimizing the energy required for that initial rendezvous. The ideal candidate is defined by a delicate balance of three factors: composition, size, and orbital accessibility. Let's examine what a perfect first partner might look like. For composition, we face a strategic choice. A metallic or M-type asteroid offers an incredible prize: high concentrations of iron, nickel, and cobalt, the very backbone of structural engineering. Imagine landing on a mountain of stainless steel already floating in space. This material would be perfect for building the robust frames of our first factory modules and the skeletal structures of early power collectors. However, metallic asteroids can be dense and tough, presenting a harder initial mining challenge. The alternative is a carbonaceous or C-type asteroid. These are darker, primitive bodies, often likened to frozen mud balls. Their treasure is not metal but volatiles. They are rich in water ice, carbon, nitrogen, and complex organic compounds. Choosing a C-type means our first mission prioritizes life support and chemistry. The water can be split into rocket fuel and breathable air, the carbon can form plastics and polymers, and the nitrogen is essential for any future habitat atmosphere. This path focuses on sustaining the human and robotic presence first, building the workshop's supplies before its tools. The trade-off is clear: metal gives you strong bones immediately, while volatiles give you the blood and breath to keep the operation alive. Size is the next critical parameter. The target cannot be too small. An asteroid only 10 meters across simply doesn't contain enough material to justify the mission. It would be exhausted after building little more than a single small satellite. Conversely, it cannot be too large. A kilometer-wide behemoth, while resource-rich, has a formidable gravity field, tiny but significant enough to complicate landing, anchoring, and any attempt to alter its rotation. It represents too much complexity too soon. The sweet spot for a pilot mission is likely an asteroid in the 100 to 300 meter diameter range. This is a substantial body containing millions of tons of usable material, enough to support decades of initial activity. Yet its microgravity is so faint that a gentle push from a robotic arm could send you on a slow drift around its circumference. It is a manageable scale, a mountain we can learn to climb. Finally, and perhaps most importantly, is orbital accessibility. This is measured by a concept called delta V, the change in velocity required to go from Earth to the asteroid and back. We need an asteroid with a low delta V requirement, one whose path around the Sun is already similar to Earth's own orbit. A perfect candidate would belong to a class known as Atens or Apollos, groups whose orbits cross or approach Earth's path. Their close approaches mean shorter travel times, perhaps only a few months with advanced propulsion, and less fuel spent on course corrections. A stable, predictable, and well-understood orbit is non-negotiable. We must be able to predict its position with centimeter-level accuracy decades in advance to ensure our delicate seed factory can rendezvous with pinpoint precision. So, what might this ideal first target be? While no single known asteroid perfectly ticks every box, we can envision a hypothetical champion. Let's call it Candidate Alpha. It is a carbonaceous chondrite, roughly 200 meters in diameter, shaped like a lumpy potato. Spectral analysis confirms abundant water ice and carbon compounds beneath its dark, dusty surface. Its orbit is an Aten type, circling the Sun in just under an Earth year, bringing it within a comfortable few million kilometers of Earth every few orbits. Its rotation is slow and stable, offering predictable sunlight patterns for solar power. This is the kind of world we would choose. It provides the volatiles to create fuel and air, securing our foothold in space. Its softer, carbon-rich material is likely easier to mine and process with our first-generation tools than solid metal. Its manageable size allows us to practice anchoring, mining, and processing on a forgiving scale. And its friendly orbit makes the journey from Earth a feasible, repeatable commute for follow-up missions carrying specialized equipment or human crews. Candidate Alpha is not a treasure chest of gleaming metal. It is a well-stocked pantry and a fuel depot, the humble but essential first stepping stone. By mastering the art of living off this land, we prove we can survive. Then, and only then, can we set our sights on the metallic giants, using the fuel and confidence forged on this dark, icy rock to build the skeleton of a new civilization. The elegance of the swarm lies in what it chooses not to be. It is not the only vision for harnessing a star. but a deliberate selection from a menu of cosmic-scale architectures, each with its own profound trade-offs. To understand why we focus on this path, it helps to briefly glimpse the roads not taken. The most iconic alternative is the classic Dyson shell, the image of a solid, rigid sphere completely enclosing the Sun. It is a breathtaking idea, a single, continuous megastructure. Yet from an engineering standpoint, it is almost certainly impossible. No known or conceivable material possesses the tensile strength to withstand the astronomical forces involved. The shell would experience immense gravitational stress from the Sun, colossal atmospheric pressure if filled with air, and catastrophic thermal expansion from the sunlight it captures. Without external support, it would buckle, tear, or collapse inward. It is a beautiful piece of science fiction, but a structural nightmare, a concept that breaks under the unforgiving laws of physics. A more plausible, yet still deeply challenging, alternative is the Dyson bubble. This concept abandons rigid connections entirely, instead using a vast fleet of independent satellites, much like our swarm. The key difference is that these units would not be in orbit at all. They would be statites, using immense solar sails to hover motionless against the Sun's gravity, holding a fixed position like a kite in a solar wind. This creates a static, non-rotating bubble around the star. The advantage is perfect, uninterrupted positioning for power transmission. The disadvantage is the staggering scale of the materials required for the sails. Each statite would need a sail many kilometers across just to generate enough photon pressure to balance its mass. The engineering demands for materials that are both incredibly thin, perfectly reflective, and durable over millennia are far beyond our current horizon, pushing this concept into a more distant technological future. Then there is the simpler, more modest idea of a Dyson ring. Imagine constructing not a full sphere, but a single, giant ring in orbit around the Sun, like a cosmic version of Saturn's rings built by intelligence. This is a more achievable first step, a colossal orbital habitat or power station. It would face fewer gravitational stability issues than a full shell and could be built with known materials. However, its fundamental limitation is one of simple geometry. A ring, no matter how vast, captures only a minuscule sliver of the Sun's total radiant energy. The vast majority of sunlight would simply stream past it, unused. While a ring could power an immense civilization, it does not represent the kind of total energy transition we are contemplating. It is a stepping stone, not a destination. This comparative view clarifies the swarm's compelling logic. It rejects the impossible solidity of the shell. It postpones the material science leap required for a static bubble, and it vastly expands upon the limited capture of a simple ring. The swarm's genius is in its incremental and fault-tolerant nature. It can be started small with a single node and grown organically over centuries. A collision or failure in one sector does not doom the entire structure. It merely creates a local repair problem. Its use of orbital mechanics provides natural, free stability without requiring magical materials. It embraces the reality of construction in space, where decentralization is not a weakness but a profound strength. In the grand design of possible futures, the Dyson swarm emerges not as the most spectacular vision on paper, but as the most plausible archetype on the drafting table, the one that bends to the laws of physics rather than demanding they be rewritten. It is the architecture of patience built one point of light at a time. The true measure of this endeavor lies not in its price tag, but in its energy balance sheet. We must confront a fundamental question: does building a Dyson swarm consume more energy than it will ever produce? At first glance, the numbers seem to doom the project. The energy cost of launching the initial seed factories, redirecting the first asteroids, and powering the bootstrap phase is almost incomprehensibly vast, dwarfing the total energy output of our global civilization for centuries. This upfront investment represents the deepest capital expenditure any species could possibly undertake. We can think of it in terms of energy return on investment, or EROI, a ratio that compares the energy you get out of a system to the energy you put into building and fueling it. For a coal plant, the EROI might be 30 to 1. You get 30 units of energy back for every one you invest. For a Dyson swarm in its earliest days, this ratio is catastrophically inverted. It is less than 1. For decades, perhaps even a century, the system would be a net energy sink, a voracious consumer of every watt we can feed it from Earth and its own fledgling operations. This is the valley of investment, a long, arduous climb where progress is measured in grams of refined metal and trickles of power, with the summit nowhere in sight. But this perspective misses the exponential nature of the project. The energy break-even point is not a distant myth. It is a calculable moment in time, the pivotal instant when the swarm's own annual energy output finally equals the total cumulative energy invested in its construction up to that date. After that point, every additional watt harvested is pure profit, a dividend paid on that initial staggering investment. Given the self-replicating, solar-powered nature of the system, this break-even would likely arrive within a few centuries of the pilot facility's launch. The calculations are complex, but the principle is simple. Once the network of factories reaches a critical mass, its growth is fueled by the sun itself, and its energy output begins to double on a regular schedule. From that moment forward, the EROI soars toward infinity. The net energy gain over the remaining multi-billion-year lifespan of our sun becomes a number so large it loses all practical meaning. It is, for all human purposes, limitless. This transforms the project from a cost into the ultimate capital investment. It is not an expense, but a foundational purchase of future capability. The energy harvested in just 1 year of the swarm's mature operation could exceed all the energy consumed by human civilization from its origins until the day of launch. What does such abundance actually enable? It powers the complete recycling of Earth's atmosphere and oceans, funding planetary-scale environmental restoration without sacrificing industrial capacity. It allows for the construction of continent-sized computational arrays, solving problems in medicine, materials science, and fundamental physics that currently require millennia of trial and error. It provides the propulsion energy to gently nudge other Earth-like planets into more habitable orbits within their own star systems, a concept known as terraforming on a stellar engineering scale. It could even fund the most ambitious project of all, the construction of interstellar arcs, self-contained worldships carrying entire ecosystems and civilizations on journeys lasting thousands of years to neighboring stars, all sustained by a steady power beam from the home swarm. These are not incremental improvements, they are transitions to entirely new categories of civilization activity, currently locked away behind the simple barrier of energy scarcity. The initial energy debt is the price of a key that unlocks a universe of possibilities, turning our solar system from a collection of isolated points into a single, integrated, and abundantly powered homeland. This immense transformation of our solar system would not go unnoticed in the cosmos. The very act of building a Dyson swarm, long before its completion, would broadcast our presence across the galaxy in a language of physics any advanced civilization could read. For decades, scientists searching for extraterrestrial intelligence have scanned the skies not just for radio signals, but for the colossal engineering projects of other species. The most promising clue they look for is an infrared anomaly. A star like our sun emits most of its energy in the visible spectrum, the light we see. But if a civilization were building a swarm of power collectors, those collectors would absorb the visible sunlight, convert a portion to useful energy, and inevitably radiate the rest away as waste heat. This waste heat would glow brightly in the mid-infrared, a thermal signature of industry. From 100 light-years away, our sun would begin to look strange to an observer with the right instruments. It would appear dimmer than expected in visible light, as more and more of its surface was shaded by collectors. Yet simultaneously, it would shine with an unexpected and growing brightness in the infrared, a telltale warmth that cannot be explained by natural astrophysics alone. This infrared excess is considered one of the most detectable signatures of a Kardashev Type II civilization, a civilization that harnesses the power of its star. Our own project, if we were to begin it in earnest, would eventually paint this exact signature across the void. Within a few centuries of the exponential build-out, as the swarm captured even a few % of the sun's output, that infrared glow would become unmistakable. We would, in effect, be turning on a cosmic beacon, announcing our arrival as a species that has graduated from its planetary cradle and is now actively reshaping its home system. This creates a profound philosophical pivot in the search for extraterrestrial intelligence. We have always been the listeners, patiently scanning the silence. But by embarking on this path, we would consciously choose to become the broadcasters, not with a deliberate message, but with the unavoidable thermodynamic consequence of our ambition. Every watt of stellar power we redirect for our use is a watt that eventually escapes as a structured infrared signature, a fingerprint of intelligence embedded in starlight. The silence of the cosmos, which feels so vast and empty, might not be a result of life's rarity but of stages. Perhaps other civilizations have already passed through this brief, luminous phase of construction, their swarms now complete and operating at such high efficiency that their waste heat signature has minimized, or they have moved onto forms of energy we cannot yet comprehend. Or perhaps they are out there right now, their suns also glowing with that peculiar infrared warmth, and we simply have not looked at the right star with the right tools for long enough. By building our own, we join a hypothetical community of cosmic engineers, participating in a project that may be a universal rite of passage for intelligent life. We shift from asking, "Are we alone?" to actively contributing an answer, ensuring that any distant watcher peering at our tiny yellow star would one day see the light of a new dawn, the gentle, persistent glow of a civilization coming of age. That gentle, persistent glow in the infrared is more than just a signature, it is a statement of identity. By choosing to build a Dyson swarm, we are not merely solving an energy crisis, we are answering a profound question about what kind of civilization we wish to become. This journey places us directly onto a framework for understanding intelligent life in the universe, known as the Kardashev scale, proposed by the Soviet astronomer Nikolai Kardashev in the 1960s. This scale measures a civilization's technological advancement by its total energy consumption. A Type I civilization has mastered its home planet, harnessing all the energy that reaches its world from its parent star, including sunlight, wind, geothermal heat, and tides. Humanity today is not yet a full Type I. We are in a transitional phase, tapping into planetary flows but still largely dependent on finite, buried reserves. A Type II civilization, the next step, achieves something truly monumental. It has learned to capture and utilize the entire energy output of its star. This is the realm of the Dyson swarm, where a species graduates from living on a planet to actively managing the energy budget of its solar system. The scale then extends to a hypothetical Type III, a civilization that commands the energy of an entire galaxy, a concept so vast it stretches our imagination to its limits. Our project, then, is the practical blueprint for crossing that threshold from Type I to Type II. This is not a minor upgrade, it is a fundamental change in scope, perspective, and responsibility. What does such a leap truly imply for humanity? First, it signifies our transition from a planetary to a stellar species. For our entire history, human destiny has been tied to the thin, fragile biosphere of Earth. Our resources, our conflicts, our art, and our dreams have all been shaped by the limits and possibilities of a single world. A Type 2 civilization breaks that solitary bond. Its economy, its infrastructure, and eventually its population become distributed across the solar system, housed in habitats we build and powered by the star we orbit. Earth remains our home, our cradle, and likely our cultural heart, but it is no longer our only address. We become citizens of a stellar commonwealth with the freedom and the obligation to think on a solar scale. This expansion is intimately linked to our long-term survivability. Confining a species to one planet is, from a cosmic perspective, an incredibly risky strategy. Planetary scale catastrophes, whether natural or self-inflicted, threaten everything we have built. By dispersing our presence across millions of independent habitats and industrial nodes, we achieve a resilience that is impossible on a single world. A disaster in one location, even a severe one, becomes a local tragedy rather than an existential threat. The civilization itself becomes antifragile, capable of enduring and learning from shocks. The energy abundance of a Type 2 stage provides the means to monitor and deflect asteroids that could threaten Earth, to potentially manage our planet's climate with precision, and to ensure that no matter what happens, the light of human consciousness does not flicker out. Finally, reaching Type 2 status grants us the potential to become shapers of our cosmic environment, rather than just inhabitants. With the energy of a star at our command, we move from being passive observers of celestial mechanics to active participants. We could contemplate projects that sound like the domain of gods, such as adjusting the orbits of planets over millennia to optimize the solar system for life, or constructing interstellar probes on a scale that ensures they reach another star with power to spare. This capability brings with it an immense ethical weight. How do we use this power wisely? Do we have the right to rearrange our solar system? The questions shift from, can we do it, to, should we do it, and for what purpose? The construction of a Dyson swarm, therefore, is far more than an engineering milestone. It is the physical manifestation of a collective decision to embrace a larger future. It is our declaration that we choose not just to survive on our world, but to thrive among the stars, to secure our legacy for eons, and to step onto the cosmic stage with both the power and the wisdom to build something worthy of our highest aspirations. The glow in the infrared is the light of that choice shining back at us from the future we dare to create. This vast vision can feel impossibly distant, a story told across centuries. Yet every epic journey begins with a single, deliberate step, a foothold established on the new terrain. We do not need to build the entire swarm to begin reaping its transformative rewards. There exists a powerful and achievable intermediate goal, a proof of concept on a grand scale that could reshape our relationship with space within a single human lifetime. We can call this the foothold scenario, the construction of a minimal viable swarm. This is not a shell or a bubble, but a purposeful constellation, a few dozen power stations built from a handful of captured asteroids, designed to accomplish two revolutionary things. First, to completely power all human industry and habitation beyond Earth's atmosphere, and second, to deliver a meaningful, clean energy supplement directly to our home planet. This foothold would be the bridge between our current planet-bound efforts and the stellar-scale future. The architecture of this foothold is elegant in its focus. Instead of billions of units, we aim for perhaps 50. Instead of capturing a planet's worth of material, we redirect a carefully selected dozen or so asteroids into stable, useful orbits. The target composition shifts decisively toward carbonaceous types, prioritizing those rich in water, ice, and carbon. Why? Because the primary goal of the foothold is not raw structural mass, but operational independence. These initial asteroids become our off-Earth gas stations and hardware stores, Their water is cracked into hydrogen and oxygen, producing all the rocket fuel needed for further asteroid retrieval, satellite deployment, and crewed missions to Mars and beyond. Their carbon provides the feedstocks for plastics, composites, and life support systems. With this closed-loop resource chain established, the economics of spaceflight are turned upside down. Suddenly, launching a mission from Earth no longer requires hauling all its fuel and water for the entire journey, a prohibitive cost known as the tyranny of the rocket equation. A spacecraft can launch nearly empty, refueling at an orbital depot supplied by our asteroid processing plants. The cost of reaching high orbit, the Moon or Mars, plummets, not by a factor of 2, but by an order of magnitude or more. The power stations themselves, perhaps 24 in the first phase, are positioned strategically. Some occupy stable Lagrange points, acting as permanent power relays. Others fly in carefully spaced orbits closer to the Sun than Earth, where sunlight is more intense, their energy beamed back to receiving stations. Each station is sizable, perhaps a kilometer across, but they are built with the robust, over-engineered designs proven by our pilot facility, favoring reliability over the ultra-lightweight perfection of later models. Their collective power output, while a minuscule fraction of the Sun's total, would be staggering by our current planetary standards. We can run the numbers in human terms. Let's say each foothold station generates an average of 5 gigawatts of continuous power. With 24 stations, that is 120 gigawatts of baseload capacity, day and night without fail. For comparison, the total capacity of all the solar panels and wind turbines on Earth today is roughly 2,500 gigawatts, but they are intermittent, subject to weather and night. Our foothold's 120 gigawatts would be constant, beamed precisely where we command it. This enables the scenario's 2 core objectives. First, it powers the off-Earth economy. Every mining robot on the Moon, every construction module in orbit, every greenhouse on a Martian outpost draws its power from this constellation. It eliminates the need to build fragile, sprawling solar arrays at each distant site or to ship nuclear reactors to every new frontier. The foothold becomes the utility grid for the inner solar system. Its energy beams the invisible power lines connecting our expansion. Second, it provides a substantial supplement to Earth. A portion of the constellation's output, perhaps 20 or 30 gigawatts, is continuously directed toward rectina farms on our planet. These could be located in remote deserts or on offshore platforms. 30 gigawatts is equivalent to 30 large nuclear power plants, but without any radioactive fuel, cooling water needs, or long-term waste. This is not enough to power the entire world, but it is more than enough to power a continent, or to provide a critical, zero-carbon baseload that stabilizes global grids as we transition away from fossil fuels. The revenue from selling this power, or the economic value of dedicating it to global public projects, creates a powerful, self-funding mechanism. The foothold begins to pay for its own expansion. Beyond the raw numbers, the foothold scenario delivers something even more critical: tangible proof. It demonstrates to governments, investors, and the global public that the core principles of the larger swarm are not science fiction, but viable engineering. It forces the creation of the necessary legal and technical frameworks in real time. How do we license asteroid capture? How do we allocate orbital slots for power beams? How do we ensure the safe operation of such a system? We answer these questions on a small, manageable scale, building the precedent and trust needed for the larger endeavor. The foothold becomes a working prototype for a Type 2 civilization, a down payment on the future that immediately begins paying dividends. It transforms the dream from a distant abstraction into a visible constellation in our sky, a string of new, steady stars whose light is not just seen, but felt, as reliable power flowing into our homes and fueling our journeys to the world's next door. The grandeur of this vision inevitably invites a chorus of skeptical questions, and they are questions we must take seriously. One of the most common critiques is that such a monumental project represents a colossal distraction, a wasteful fantasy that diverts resources and attention from the urgent, pressing problems we face here on Earth. Why pour trillions into capturing asteroids when billions still lack clean water, stable food supplies, or reliable energy? This is a powerful moral argument, grounded in the undeniable needs of the present. Yet it rests on a false dichotomy, the assumption that we must choose between solving Earth's problems and building a future in space. In reality, the technologies demanded by the swarm are precisely the technologies that would accelerate solutions on our home planet. The relentless drive for closed-loop life support systems, where every drop of water and molecule of air is reclaimed and recycled, would gift us with hyper-efficient systems for managing resources in our most challenged regions. The advanced material science required for structures that last centuries in the harsh vacuum would revolutionize construction, medicine, and energy storage on Earth. The project would not be a diversion but a catalyst, creating a rising tide of innovation that lifts all boats. Furthermore, the swarm's ultimate purpose is to solve the foundational problem of energy scarcity, the very root of so many geopolitical and environmental challenges. By mastering the ability to generate and distribute clean, abundant energy, we remove the primary driver of resource conflict and create the economic surplus needed to address poverty, education, and healthcare on a global scale. It is not an either-or choice, but a strategic investment in the tools that make solving all other problems more achievable. Another profound skepticism targets the very heart of the proposal, the concept of exponential self-replicating automation. To many, this sounds like a dangerous fantasy, a leap of faith into a future where machines we cannot fully control build an infrastructure we cannot fully comprehend. The fear of a runaway replication event, a mechanical cancer consuming the solar system, is not a plot from a science fiction novel, but a legitimate engineering concern that must be designed against from the very first line of code. The counterpoint lies not in denying the risk but in embracing the discipline it demands. We would not be building sentient, general-purpose robots with the open-ended goal to replicate. We would be constructing highly specialized, single-purpose factories whose replication function is a tightly controlled subroutine, governed by hard-coded limits and external authorization. Think of it not as unleashing a new form of life, but as programming a very slow, very precise industrial printing press. Its instructions are etched into radiation-hardened, non-rewritable memory. Its ability to build the most complex components of itself, the central computers or the finest manipulator arms, would be deliberately bottlenecked, requiring parts or authorization codes that only human stewards can provide. The goal is to make the system usefully productive but incapable of open-ended evolution, turning the dream of exponential growth into a carefully managed tool, not an autonomous force. Perhaps the most daunting obstacle is not technological but human. The argument that our political fragmentation, our national rivalries, and short-term economic cycles will forever prevent the coordination required for a centuries-long, globally funded project carries a heavy weight of historical evidence. We struggle to agree on climate treaties or international aid, so how could we possibly agree to build a solar power grid? This critique touches on the deepest challenge of all, the need for a civilization to act as a civilization. The counterargument begins with a shift in perspective. Such a project would not begin with a global vote to fund the entire endeavor. It would start, as all great ventures do, with a small consortium of willing partners, perhaps a coalition of spacefaring nations and private enterprises funding a demonstrator mission. Its initial goal would not be to build the swarm, but to prove a closed loop of resource extraction and manufacturing in space. Once that loop is closed, the economics change. The project begins to generate its own value, selling fuel, materials, or power beamed to early customers like lunar bases or scientific outposts. It transitions from a pure cost center to a revenue-generating utility. This creates a new model for participation, not based on shared ideology, but on shared infrastructure and economic benefit. Nations or corporations could buy in as customers or investors, securing a share of the output or a slot on the orbital highway. The political framework would evolve pragmatically, much like the rules for aviation or the internet did, driven by the practical need to make a useful system work for everyone. It would require new institutions, but history shows we are capable of building them when the incentive is clear enough. The existential necessity of becoming a spacefaring civilization provides the ultimate incentive. Confining our species to a single planet is an immense and unnecessary risk. By building a resilient solar system-wide presence, we ensure that no single catastrophe, whether natural or self-inflicted, can end the human story. This long-term perspective is not a luxury. It is the ultimate act of responsibility for generations we will never meet. The political will to begin may be the hardest part to summon, but it is also the part that defines what legacy we choose to leave in the cosmos, a testament to division or a monument to our collective potential. The blueprints are drawn, but the construction site is still empty. The journey from a single planet to a solar civilization begins not with a grand declaration, but with the quiet, practical work we choose to fund and pursue today. Every mission we launch, every treaty we sign, every prototype we test is a brick in the foundation of that future, whether we consciously acknowledge it or not. Our current era of space development is not separate from the vision of a Dyson swarm. It is the unconscious, essential first phase of a project that will unfold over millennia. We are already gathering the tools, and the first steps we take now will determine if we walk this path wisely or stumble before we truly begin. The most urgent and immediate action is to complete the map. We cannot use what we cannot find. While projects like NASA NEO Surveyor are vital for planetary defense, our ambition demands a more dedicated and continuous census. We need to champion and fund a constellation of space-based telescopes whose sole purpose is to find, track, and characterize near-Earth asteroids for their resource potential. This goes beyond just spotting a rock. It requires determining its size, shape, rotation, and most importantly, its precise composition. Is it a metallic treasure trove or a carbonaceous reservoir? We need to know, and we need that data in a public, searchable catalog. This is not glamorous work, but it is the indispensable groundwork of cosmic logistics. Without this detailed inventory, any future mission is a shot in the dark. By investing in these survey missions now, we are not just protecting Earth, we are opening the first page of the solar system's industrial directory. Simultaneously, we must learn to live off the land beyond our atmosphere. This is the field of in situ resource utilization, or ISRU, and it is being pioneered on the frontiers we can already reach. The Artemis program's goal to establish a sustained presence on the Moon is a perfect test bed. Experiments to extract water ice from permanently shadowed lunar craters are not just about supporting astronauts, they are rehearsals for the exact same processes we will use on carbonaceous asteroids. When a prototype rover heats lunar soil to release trapped oxygen, it is perfecting the thermal processing techniques our future factories will rely on. We need to expand these efforts, sending more robotic prospectors to both the Moon and carefully selected near-Earth asteroids to conduct real-world mining and processing trials. Each successful test, each kilogram of water extracted or metal refined in space, validates a link in the chain and drives down the perceived risk for the next larger investment. The leap from processing raw materials to building functional objects in space is the next great hurdle. We must move from theoretical models to orbital prototypes. This means funding and flying demonstrations of key manufacturing technologies in the microgravity environment where they must eventually operate. Imagine a small satellite launched within the next decade, equipped with a three-dimensional printer that uses simulated asteroid regolith or pre-loaded metal powder to fabricate a simple structural beam. Another could test the deployment and alignment of a thin-film solar array manufactured on orbit. A third might demonstrate robotic assembly, where two separately launched components autonomously dock and connect to form a larger structure. These are not full-scale factories, they are pathfinder missions designed to fail in informative ways and teach us the 1,000 subtle lessons that no ground-based simulation can provide. Each successful prototype shrinks the unknown, turning a daunting leap of faith into a series of manageable, incremental steps. None of this technical progress will matter if the legal and political framework remains a tangled web of uncertainty. The current space law regime, built for an age of exploration, is ill-equipped for an era of industrialization. We need clear, forward-looking international agreements on the use of space resources. The goal is not to carve up the cosmos for national claims, but to establish transparent rules of the road that encourage responsible investment and prevent conflict. How do we register a claim to extract resources from a specific asteroid? What safety and environmental standards must be met? How do we coordinate traffic in crowded orbital lanes? These questions need answers before the first commercial mining vehicle leaves the launch pad. Diplomats and lawmakers must work alongside engineers, crafting treaties that balance the incentive for innovation with the imperative for peaceful, sustainable development. This is the unglamorous software of our future, the legal code upon which the physical hardware will depend. When you step back, these seemingly disparate efforts, the surveys, the ISRU experiments, the manufacturing demos, and the diplomatic negotiations are not random pursuits. They are the unconscious first phase of the millennia-long project. Every robotic probe that lands on an asteroid is a scout for our future industrial nodes. Every watt of power generated on the Moon from local resources is a miniature version of the swarm's energy loop. Every international meeting on space resources is a rehearsal for governing a solar system-wide civilization. We are already building the future, one grant, one mission, one treaty at a time. The choice before us is not whether to begin, but whether to recognize these steps as part of a coherent, purposeful journey. Will we continue with fragmented, short-term goals, or will we finally connect the dots and see the constellation they are meant to form? The first brick of the Dyson swarm may not be laid for a century, but the quarry from which it will be cut is being surveyed right now in the silent dark between the stars. The roadmap is now complete, from the first survey telescope to the final beam of power lighting a distant world. We have traced each link in a chain of logic, where one step naturally enables the next. Redirecting an asteroid provides the materials to build a factory, which builds the machines to capture sunlight, whose energy builds more factories in an accelerating loop of creation. This is not magic, nor is it a sudden leap into a science fiction future. It is a staggering but coherent engineering project, broken down into phases that each build upon proven principles of physics, robotics, and orbital mechanics. The true revelation is that the greatest obstacle was never the technology itself, but the scale, and the scale is defeated by patience and exponential growth. By using the resources already in space, we bypass the paralyzing energy cost of lifting a planet's worth of material from Earth's gravity well. This transforms the endeavor from an impossible fantasy into a patient, logical series of problems we can already begin to solve. The path it charts leads to more than just immense power. It is the blueprint for a sustainable transition to a truly post-scarcity energy civilization. When the basic cost of energy approaches zero, the fundamental economics of scarcity that have shaped all of human history begin to dissolve. This abundance powers the solutions to our planetary challenges, fuels the exploration of our solar system, and secures the long-term survival of our species across countless independent habitats. It fundamentally alters humanity's place in the cosmos, elevating us from inhabitants of a single world to stewards of a star system, with the capability and the responsibility that such a role entails. This journey will not be measured in years but in centuries. It demands a perspective that sees a project begun today as a gift to descendants 10 generations removed, a testament to the power of long-term thinking. The call, then, is not for us to complete the swarm, but to become the generation that chooses to lay its foundations. Our task is to build the catalog, to test the prototypes, and to forge the agreements. We must look up and with clear eyes identify not just points of light, but the very first asteroids, the raw stones from which a new kind of future will be built.